goes to Moscovia. So I think you could start.
Okay. So, shall I?
Yeah.
Okay. Okay, well, I'll waste some time by thanking you, Joshua, for organizing this meeting. It's been a long road.
And not to Tipperary.
Indeed, thank you very much. I know that you've worked really, really, really hard to prepare for this, and it's been hard work, stressful, but it's happening. So congratulations. Yeah. Yes.
Thank you.
Okay, so I'm going to assume that there are some people in the room who are less familiar with PT, and so I will say some elementary things earlier in the talk. And let's see, does this work? Yeah. So the point of this talk is that PT symmetry is an extension of conventional quantum theory in the complex domain. And as you all know, mathematicians have found it enlightening to extend the real number system to the complex number system because it teaches us stuff about the real number system. But by extending conventional physical theories into the complex domain, we as physicists can also benefit, and we're going to see that the benefit is very interesting. We're going to learn how to control instabilities in systems that are unstable in the real domain. Okay, so theories that look unstable to us, by re-examining them in the complex domain, we're going to see that they are not unstable. So here's the basic idea. If you extend the real numbers to the complex numbers, you lose the ordering property of the real numbers. You know that when you go from the real number system to the complex number system, all of the rules of arithmetic remain intact. You know, you still have the commutative law and the associative law and the distributive law and so on. But there's one thing that you lose, and what you lose are these symbols, okay? So we have no inequality. The complex number system is perfectly democratic. And when you say that a physical system is unstable, how do you know it's unstable? Well, you make an argument that makes use of an inequality. You say that the potential is unbounded below. That makes use of an inequality. But you can no longer use that inequality in the complex domain. And so this is the underlying reason why systems that look unstable are actually, you're going to see some systems are not unstable. Okay? So here's the outline of my talk. Okay? And that's as much as I can say. So here's a little bit of background material. Here's an example of a PT symmetric Hamiltonian. This is not conventionally Hermitian, and that's obvious. And you might say, if you haven't seen PT symmetry, you might say, well, the way I see it, this theory is crazy. However, you can see that this Hamiltonian, although it is not Hermitian, it is PT symmetric because under parity P, X changes sign and also P changes sign. Under time reversal T, X goes into X, but P goes into minus P, and I goes into minus I. Okay? And therefore, the product IX cubed remains invariant under PT. And so this is a PT invariant Hamiltonian. Okay? Why does T change the sign of I? Well, Mr. Wigner helped to explain that to us. A simple explanation is that you would like the Heisenberg algebra, which underlies quantum mechanics, to remain invariant. Okay? And under PT, the left-hand side, or under time reversal, the left-hand side changes sign, because P changes sign. So the right-hand side better change sign as well. And so I has to change sign. Or you could just look directly at the Schrodinger equation, and you should look just at the Schrodinger equation. Okay, and if you look on the right-hand side, you see that time is associated with an I, okay, and if you want to change the sign of t, you have to change the sign of I. Okay, so that Hamiltonian, the Ix cubed Hamiltonian, is just one of a large class of Hamiltonians, and this is a whole continuous family of Hamiltonians, and the Ix cubed Hamiltonian corresponds to epsilon equals 1. Okay, and if you make a plot of the eigenvalues of this system of Hamiltonians, you see that when epsilon is positive, the eigenvalues are strictly real and positive and discrete. Okay, so PT symmetric quantum theory is an extension of quantum mechanics into the complex plane, and so what I mean by that is the following, that if you take a conventional Hamiltonian, which is Hermitian, H is equal to H dagger, dagger in this case means transpose and complex conjugate. This condition is a very powerful condition, and it guarantees that the energy is real and probability is conserved. But I would argue that this axiom is a rather mathematical axiom, and it doesn't, at least when you say transpose and complex conjugate, it doesn't exactly sound like physics. So what we're doing here is generalizing Dirac hermeticity and replacing it by a weaker condition. And the weaker condition is PT invariance. And I say that this condition is not just weaker, but it's more physical because both P and T are elements of the Lorentz group. Okay? And this is something that Philip is going to emphasize very strongly in his talk on relativistic quantum mechanical PT symmetric theories. So there have been lots of developments in the last decade and a half on PT quantum theory. There have been over 24 international conferences and symposia, which is amazing, absolutely amazing. There have been over 2,000 published papers. There have been lots of experimental results in the last 5 years, and I would say that PT is doing very well. Okay? In fact, last year alone, in 2014, there were 20 papers in high-impact journals. So what I mean by high impact, I mean Physical Review Letters, Nature, and Science. And that is, at least these are the papers that I found. There may even be more that I haven't found. So again, to emphasize, the spectrum of this Hamiltonian, p squared plus x squared, the harmonic oscillator, deformed into the complex domain with a term Ix to the epsilon, has a spectrum that is discrete and real and positive, and parity symmetry, by the way, is broken. And if you are interested in a rigorous proof that the eigenvalues are real, you can read the work of Dorey and Dunning and Tateo. Okay? Well, however, if you go back to this Hamiltonian, you might say, wait a minute, just a moment, this doesn't look right, because if I take epsilon equals 2, then this Hamiltonian reads p squared minus x to the 4. So we have a potential which is an upside-down potential. How could this potential possibly have real positive eigenvalues? We're talking about an upside-down potential. Okay, so this is an unstable theory. You know, this is upside down. How can you possibly make sense of this theory? Okay, it certainly looks like this potential is unstable on the real axis. How can it have bound states? Okay, well, this is the simple intuitive argument. Let's begin with the classical harmonic oscillator. The way you teach it is to say, look, the Hamiltonian is p squared plus x squared. This describes a particle in a right side up quadratic potential well. The particle goes back and forth in this potential? Well, it stops at the turning point and goes back here, and it stops at this turning point and goes back and forth. And this is simple harmonic motion, okay? So this is the classically allowed region. This over here is the classically forbidden region, okay? And just to explain the difference between classically allowed and classically forbidden, this is, I think, the best way of explaining it to students. So the question is, what happens if you start a particle in the classically forbidden region? Well, if you put a particle over here, then x is greater, x at time 0 is greater than the turning point. So x squared is greater than the energy. So p squared must be negative. How could p squared be negative? Well, the answer is that p is imaginary. The velocity of the particle must be imaginary. So if you start a particle in the classically forbidden region, the particle is going that way into the complex plane, okay? And if you then solve Newton's equation of motion, you find that the particle travels in an ellipse, okay? And what you learn is that this back and forth motion that you study in an elementary physics class is actually not back and forth. It's actually going around in an ellipse. And what that back and forth motion is really a degenerate ellipse, okay? Well, if you then increase epsilon, and you say epsilon is now 1, so we're back to the Ix cube theory, now the turning points move down into the complex plane. There are 3 turning points altogether. And you still have a back and forth motion between the turning points, okay? And near the turning points, you have deformed versions of the original ellipses, okay? And if you go to a p squared minus x to the 4 theory, you now have 4 turning points. You have a back and forth motion between the turning points, but the deformed ellipses look like this, okay? And now, if you try to understand how this upside-down potential behaves, what you need to do is to start in the complex plane and approach the real axis. And as you approach the real axis, what happens? These closed trajectories get bigger and bigger and bigger. And so here I am starting in the upper half plane. I'm approaching the real axis. And you have huge trajectories, but the fact is that the amount of time it takes to go around each trajectory is always the same. And this is true by Cauchy's theorem. Okay? It's just a simple application of Cauchy's theorem, and which is the integral representing the time of flight. Okay? So as you approach the real axis, the particle goes way out to infinity, all the way around, and comes back up the negative axis. Okay? So is this an unstable potential? No, it isn't. In fact, it is not unstable. The reason it's not unstable is that if you balance a particle right at the origin on this upside-down potential, it goes off to infinity, but it reaches infinity in finite time. And then it comes back up from minus infinity and comes right back up and returns to the origin. Okay? So you can make a plot of the probability. This is the classical probability density of a particle on the real axis. And what you see...
So Carl, you're doing classical mechanics.
Right now I'm doing just classical mechanics.
In complex paths.
That's right. That's right. So as you approach the real axis, what you see is that the classical probability density is 1 over the velocity. Okay? You are less likely to find the particle if it's going faster. That's why when you're driving, especially in Harvard Square, it is necessary to go as fast as possible so as not to have an accident, because the probability of finding you in Harvard Square goes down. Okay? So the probability of finding a person is greatest at the origin. Okay? So what we have is a localized classical particle. And the classical particle, even though we're on an upside-down potential, is actually localized at the origin. Okay? And in fact, you can see what is happening in the complex plane. If you make a three-dimensional plot of the classical probability, the particle whizzes around in the complex plane, and the probability of finding it there approaches 0. Okay? And the probability of finding it over here on the real axis at the origin is spiking. Okay? So the only difference when you quantize the system, if you use Bohr-Sommerfeld quantization and you do an integral around any one of those loops and you set it equal to n plus a half pi, okay, what you find is the eigenvalues, the energy levels that I showed you at the beginning of the talk. Okay, those are the energy levels. And so the instability at x equals 0 is tamed. This is not an unstable theory. This is a perfectly stable quantum theory, and it has bound states. Particle is localized at the origin. And the only difference between the classical probability and the quantum probability is that the classical probability has one spike, but the quantum probability has a bunch of, depending on which state you're in, has a bunch of peaks. That's all about the origin. Okay, so one other introductory remark is that there is obviously a transition at epsilon equals 0. And epsilon equals 0 is the PT boundary. If you set in this Hamiltonian, if you set epsilon equals 0, that is the one case where you have a conventional Hermitian Hamiltonian, the harmonic oscillator. And if you go below epsilon equals 0, what you see is this phenomenon. A lot of people like to call this exceptional points here. And this is where the energy levels come together and become degenerate. Okay? And you see that these points, these values of epsilon at which these degeneracies occur, these values of epsilon approach the origin, approach epsilon equals 0 from below. Okay? So this is called the region of unbroken PT symmetry, where the eigenvalues are real, and the region of broken PT symmetry, where some of the eigenvalues are complex. Okay? Okay, so you should remember there's a region of broken PT and a region of unbroken PT. Okay? So the condition of PT symmetry is weaker than the condition of hermeticity. All eigenvalues E of a Hermitian Hamiltonian are real. They are real. But for PT symmetric Hamiltonians, only the secular equation, which is the determinant of H minus I times E equals 0, is real. Only this equation is real. So this equation can have all real eigenvalues, or it could have some complex eigenvalues. And you don't know before you begin working which is the case. But in general, unlike Hermitian Hamiltonians, there are always two possibilities. PT symmetric theories can have an all real or a partially real spectrum. Okay? They can either have an unbroken or a broken region of PT symmetry. And this is an example of two possibilities that you have to choose between. Okay? So Hermitian Hamiltonians, I would argue, are sort of boring because the eigenvalues are always real and nothing interesting happens. Okay? But PT symmetric Hamiltonians are quite astonishing because you see this transition between parametric regions of broken and unbroken PT symmetry. And this can be observed experimentally. As soon as you have a transition, you should go and look for it in the laboratory. Okay? So here's a quick intuitive explanation of the transition. Imagine you have a closed box with gain. So stuff is going into the box. The Hamiltonian for this system is, of course, non-Hermitian because probability density is not conserved. And you can write the Hamiltonian just as a 1-by-1 matrix, A plus IB. Okay? And we have a complex Hamiltonian here. Okay? So now, why not add another box? So here's a box where stuff is going in, and another box where stuff is going out. This box has gain, this box has loss, and the combined Hamiltonian is now a two-dimensional system. Okay? Here's the box with gain, and here's the box with loss. Okay? And the Hamiltonian for this system is, of course, non-Hermitian, but it is PT symmetric. Okay? And the simple way to see that it's PT symmetric is that under parity, you exchange the two boxes. And under time reversal, in becomes out, and out becomes in. That's all. Gain becomes loss, and loss becomes gain. Okay, now let's couple these boxes with a coupling strength G. So now we have an off-diagonal element coupling these two systems, which are no longer independent. Okay, and this system can be in equilibrium for sufficiently large coupling, and to see that, all you need to do is to calculate the eigenvalues. So you calculate the determinant of H minus IE. This is the secular equation, and as I said, the secular equation is real, and if you find the roots, these are the roots, okay, and you notice that if G squared is bigger than B squared, G is big enough, then this square root is real and the eigenvalues are real, okay, and that is the unbroken region. So, and furthermore, you can see that that Hamiltonian is PT symmetric because T is complex conjugation, and we can define parity to be this 2 by 2 matrix. Okay, and this is the transition from complex eigenvalues to real eigenvalues, and you've seen this transition in many papers. Okay, so to close this sort of these very elementary introductory remarks, PT symmetric systems lie between closed and open systems. So PT symmetric systems are open in the sense that they're connected to their environment. They have stuff going in and stuff coming out. So PT symmetric systems are a kind of an open system. But on the other hand, there's a balance between loss and gain. And as a result, especially if you're in a region of unbroken PT symmetry, PT symmetric Hamiltonians behave very much as if they are Hermitian. They look like they're Hermitian. They have all real eigenvalues. Okay? So these are the Hermitian Hamiltonians. These are the Hamiltonians used to describe closed systems. These are typical non-Hermitian Hamiltonians that you might use in a scattering experiment or to describe a decay of a particle. And here you have a PT symmetric Hamiltonian that is sort of midway between. It can behave like this if it has a broken PT symmetry, and it can behave like this if it has an unbroken PT symmetry. Okay, so just a quick review or partial review. It is absolutely incredible to me, because I come out of mathematical physics, it's incredible that there have been wonderful, beautiful experiments published over the last half decade in which PT symmetric systems have been observed experimentally. Here is the first observation of the PT transition using waveguides. Here's the second, which was in fact done partly in Israel by Segev. This is a study of PT symmetric diffusion. Here's a study of PT symmetric optics at Caltech. PT symmetric superconducting wires. PT symmetric microwave cavities. PT symmetric cavity lasers. There's been a huge amount of work done at Yale on PT symmetric lasers and unidirectional invisibility. PT symmetric photonic graphene done at the Technion. This is more work on lasers done in Vienna, Princeton, Yale, and Zurich. Multiple PT symmetric waveguides. More work on superconducting wires. PT symmetric NMR. And this is a beautiful experiment. It was so beautiful. I read this paper and I said, wow, this is really ingenious. This is work that was spotlighted as exceptional research. And when I read this paper, I said, gee, all you need is an oscillator, right? So I said, why don't we make an oscillator? Let's take a pair of coupled pendula, and one pendulum has loss, and the other pendulum, here, this pendulum has loss, this pendulum has gain. All you do is you remove some of the energy from the X pendulum and transfer it to the Y pendulum. And here are the pendula, and you can see the PT phase transition. You can just watch these pendula going back and forth. This is why science teachers should not be given playground duty. We spend a long time watching these pendula swing back and forth. Here's a more sophisticated experiment involving parity time symmetric whispering gallery microcavities. And this is work that was done at my university, which is very nice. And these are actually whispering galleries. You can get a whispering gallery waved to travel around and around this solid state gadget. It goes around 1 million times before it's absorbed. It's absolutely beautiful work. And here you see the PT phase transition. Okay? So PT symmetry, so that's just a review now. So what I want to argue is that PT symmetry can control instabilities. Physical systems that you might think are unstable become stable in the complex domain. And here's a very simple example of it. If you look at the last chapter of Jackson, you will see that there's a discussion of the electromagnetic self-force and runaway modes. And in the non-relativistic limit, you'll see that there is a third-order differential equation. What you have here is an oscillator, just x dot dot plus kx, okay? And a three-derivative term that corresponds to the back reaction force, the electromagnetic self-force. And there are runaway modes. This system is unstable, okay? However, if you add another equation with the opposite sign of the three-derivative term here, these systems together are actually Hamiltonian. And this is the Hamiltonian here that gives rise to those equations, okay? And you can understand these runaway modes simply as an example of a broken PT symmetry. This system is in a broken PT symmetric phase, but if you now couple the system, you can send it into an unbroken phase, and the runaway modes disappear. Okay? So this is how you tame an instability, very big, frightening instability. Okay? So I want to give you 4 examples, older examples, of instability problems. I talk very briefly about the Lie model, the Pais-Uhlenbeck oscillator, the double scaling limit in quantum field theory, and nonlinear differential equation eigenvalue problems. So this is a summary of older work. No, actually, there were 5 stooges. Okay? However, they're called the 3 stooges. It's like the trilogy, okay, which consists of 4 books. Okay. So the Lie model, this is a rather old example that we worked on, is a beautiful example of a quantum field theory with an instability. It describes a universe in which there are just 3 particles, and they're called V, N, and theta. And you have to imagine that in this universe, the V particle turns into an N and a theta, and the N and the theta turns back into a V. That's all. And the Hamiltonian that describes this interaction consists of a free Hamiltonian that just counts up the numbers of V's, N's, and thetas, and an interaction Hamiltonian which creates a V after it destroys an N and a theta, or it creates, it destroys a V and creates a theta and an N. Okay? This is, the Lie model was proposed by T.D. Lie in 1954, but in 1955, Shalane and Pauli wrote a paper and said this is wrong. This is completely wrong. And the reason is that if you renormalize the theory and you express the unrenormalized coupling constant as a function of the renormalized coupling constant, so you measure this in the laboratory, what you can find is that the square of the unrenormalized coupling constant is negative. Well, if the square of the unrenormalized coupling constant is negative, then the unrenormalized coupling constant is pure imaginary. And if you go back to the Hamiltonian, okay, here is the unrenormalized coupling constant, and it's multiplying a cubic Hamiltonian. Okay? So we have, in effect, an IX cube theory. Okay? Well, what Shalane and Pauli said was this is no good after renormalization. So renormalization puts an instability into the theory. Renormalizing the theory is a very bad thing to do because it introduces an instability, and as a consequence, you violate unitarity. Okay? and you have ghost states. Okay, and this is a summary of that work by Salam, in which he said this is terrible, okay, and this is a very serious problem. The authors discover the remarkable result that if G is greater than G critical, there's a new eigenstate which is a ghost. Unitarity is violated. This is terrible. However, you can read what Barton says about this, and non-Hermitian Hamiltonian is unacceptable, partly because it can lead to complex energy eigenvalues, but chiefly because it implies a non-unitary S matrix, which fails to conserve probability and makes a hash of the physical interpretation. And this is the epitaph for the Lie model. But this is a really hard problem, and lots of people, Pauli himself, Heisenberg, Wick, Sudarshan, lots of people worked on this problem. And the problem remained unsolved. As far as people knew, this was a bad theory. This is a really hard problem, okay, as you can see. Now, the solution to this problem is over here, okay? And we also found the solution to that problem. All you need to do is some ghost busting, and all you need to do is to recognize that when you renormalize the theory, it becomes PT symmetric. And you violate conventional hermeticity, but you don't break PT symmetry, and in fact, you're in an unbroken PT symmetric regime, and there's nothing wrong with the theory, nothing at all, okay? Here's a second example, and this is something I worked on with Philip for a while. The Peiss-Uhlenbeck model has a very serious problem. It has a fourth order field equation, okay? And when you calculate the propagator and you put it, you write it in separated partial fraction form, you see the appearance of a ghost, at least what people thought was a ghost. But there isn't a ghost. In fact, here you have again a PT symmetric theory. So we looked very hard for a solution. We found it right there, okay? And the solution is that this is a PT symmetric theory and there are no ghosts, okay? Third example involves the double scaling limit in quantum field theory. If you look at the large N limit of, say, a phi to the 4 theory, you find that you get the wrong sign. You get a wrong sign potential. You get an upside down potential theory. But in fact, there isn't anything wrong with this theory. This is merely a PT symmetric theory. And we have written 2 papers on this, showing that, in fact, there really isn't a problem. This is an upside-down potential, but I have already talked about upside-down potentials. So PT symmetric quantum mechanics comes to the rescue. And one last example involves, this is a more mathematical example, it involves instabilities of nonlinear differential equations. In fact, the Painlevé transcendents, there are 6 of them, have fundamental instabilities. And these instabilities can be tamed and understood quantitatively by using PT symmetric quantum theory. And we've written 2 papers on this, and there's a 3rd paper in preparation. And I'm not going to tell you about this at all now because I spoke on it in Palermo, but I'll just say that the instability of Painlevé 1 amazingly can be explained by looking at the large eigenvalues of the cubic PT symmetric Hamiltonian. That is, Painlevé 1 corresponds to epsilon equals 1. And all you need to do is to use this theory. This theory is a linearization of the first Painlevé transcendent. Okay? So you remember the PT symmetric cubic Hamiltonian. And Painlevé 2 can be explained by looking at the large eigenvalues of the quartic PT symmetric Hamiltonian, the minus x to the 4 Hamiltonian. So Painlevé 2 corresponds to epsilon equals 2. And you remember that quartic upside down Hamiltonian. So Painlevé 4 corresponds to a sextic PT symmetric Hamiltonian, which is this. So Painlevé 4 corresponds to epsilon equals 4, which is quite remarkable. Okay? And if you like, later on, I'll tell you some conjectures about why there are only 6 Painlevé transcendents, but there's a continuous number of values of epsilon, but we can save that for later. Okay. So here are, I'm just going to conclude by a very brief mention of 3 recent PT research problems And this is very relevant to the talk that Philip is going to give tomorrow. Okay. So the three problems involve conformal Liouville quantum field theory and supergravity, and finally a discussion of the Higgs vacuum. Very brief remarks. Okay. So Liouville quantum field theory, we looked at something called time-like Liouville conformal logarithmic quantum field theory. It's a very long word. But basically, this is a Lagrangian that contains a term of the form that contains the field multiplied by e to the I times the field, and also e to the I times the field. Okay? And this can be, this term is the important term. This can be eliminated just by translating the field. So the corresponding quantum mechanical theory is p squared times x times e to the ix. Okay? This is a very interesting Hamiltonian that has not been had not been studied before. It's very interesting because if you just take a potential of the form Ix, there are no eigenvalues at all. And that's because this is an argument that involves the number of Stokes wedges, which I won't go into here. But if you look at the classical paths for this potential, the classical paths are all open. Okay? And in order to get real eigenvalues, you must have closed classical trajectories. Okay? So the paths do not close and there are no eigenvalues. And the fact that there are no eigenvalues was proved rigorously by Herbst. Okay? If you look at just the e to the ix potential, this is a periodic potential, and if you look at the classical paths, they just go on forever and ever. They're just periodic, like this. There are an infinite number of turning points. The classical paths, again, do not close. They just go up and down the parallel to the, or they go, not parallel to, but they go along the real axis and they never close. However, if you look at potentials of the form x e to the ix, you get beautiful classical paths, which are really remarkable. You get one system of classical paths that close like this. Okay? One bunch of classical. Then you get a bunch of classical paths that close like this. Okay? That enclose this pair of turning points. And then you have classical paths that enclose this PT symmetric pair of turning points that go like this. Okay? And they only enclose, each set of classical paths only encloses one pair of turning points. Okay? So the paths form families that encircle pairs of turning points. And the families are separated by separatrices, which are these red dashed lines here. Okay? And if you try to quantize the system, you find something really beautiful. The paths are only in one sheet of a Riemann surface, but there are infinitely many, infinitely thin Stokes wedges. And each Stokes wedge corresponds to a different quantum spectrum. Okay? So in the nth, so if you look at the nth eigenspectrum, in the mth Stokes wedge, you see that the eigenvalues asymptotically, the WKB approximation, has this beautiful form. So it looks like a square well, okay, as far as M is concerned, and a Balmer spectrum as far as N is concerned. It's really very, very pretty, quite remarkable. Okay, so you have an infinite number of independent, topologically independent theories, and all coming from an x e to the ix potential. It's quite beautiful. Okay, so a remark, just a brief remark about supergravity. If you read some papers on supergravity, you'll see that the renormalized effective potential, which involves a gravitino-condensate field, has the form of a minus phi to the 4, an upside-down potential, which I've talked about before, times log of I phi. And this is PT symmetric. And until we worked on this, I think nobody had looked at logarithmic PT symmetric potentials. This is what the Hamiltonian looks like in the corresponding quantum mechanical theory. So instead of p squared minus x to the 4, it's p squared minus x to the 4 log of ix, which is unstable. Okay? And so to prepare for studying this, we made up a toy model. We put in a plus sign here instead of a minus sign. And then we looked at the classical paths, and you notice that the classical paths are all closed, which suggests that the eigenvalues are real. Okay? Remember, closed orbits mean real energies, but there's a logarithm. So there's a branch cut on the imaginary axis.
Is that a theorem?
In one dimension, I believe it is. In higher dimensions, it isn't.
Isn't the statement in general that real energies must have closed orbits, rather than
No.
closed orbits must have real energies?
Well, no. No to both. Not in higher dimensions, but in one dimension, yes. Okay? So the question is, what happens if a trajectory should happen to hit this branch cut? And now this is what happens. It's quite beautiful. The trajectory crosses the branch cut, the logarithmic branch cut, visits 3 sheets of the logarithmic Riemann surface, but it is still closed. Okay? And so, in fact, this is the WKB calculation of the eigenvalues. And this is a table comparing the numerical eigenvalues with the WKB, and the approximation is very accurate. So then we went to the supergravity model with the minus sign here, and the results are similar. They're almost the same. So here are the closed classical trajectories. And if you cross the branch cut, this is what the trajectory looks like. It's very complicated, but it still visits only 3 sheets of the Riemann surface. It's left-right symmetric, PT symmetric, and closed. The eigenvalues are real, and I'm going to show you the eigenvalues. Here they are. And I wanted to show you this because this looks very much like the graph of the eigenvalues that I showed you at the beginning of this talk. You notice that the eigenvalues are all real, so to get this minus x to the 4 log of ix potential, we did exactly the same thing as you do for an upside-down x to the 4 potential. We let epsilon go from 0 to 2, and you notice that the eigenvalues are all real. But the one change is that instead of the thing breaking down because of what Mr. Herbst tells us at -1, it breaks down at -2. Okay, very interesting. So the plot looks almost the same, and at epsilon equals 2, all the eigenvalues are real. Okay, so this is what looks like an unstable theory is not unstable. So finally, the last remark is this. What about the Higgs vacuum? In the standard model of particle physics, phi is the Higgs field, and this is the effective potential, okay, if you renormalize the theory. So at the level, at the tree level, for the Higgs model, you have a plus phi to the 4 theory, no problem. And in fact, you have a Mexican hat potential. But if you renormalize, and if you read this very long paper by Mark Schur, classic paper, what he shows is that if you renormalize the theory, just as in the case of the Lie model, you have a disaster. What is the disaster? You get a minus sign here. The minus sign comes when you're calculating fermion loops, and in fact, as Philip knows, this is the top quark that screws everything up. Okay?
This is just the one loop.
It's the one loop calculation. And now the sign changes and we have an unstable effective potential. So the universe is unstable and we're all going to die. Okay, this is very bad news. Okay, and at a recent conference I went to a few months ago, the calculations that people were doing all agreed we're all going to die. But the question is, how long will it take before we all die? Okay, and there are estimates that, well, it is very long. In fact, if you adjust the parameters in the standard model, many of which are not even known, the values are not known, it is conceivable that the lifetime of the universe will be long enough that we'll at least have time for lunch. Okay? But I want to give you a different picture. So this is an unstable effective potential. It's an upside-down potential. But it's more interesting because there's a logarithm. It's not just minus x to the 4, but it's minus x to the 4 log x. And this is really for Philip. Okay, I hope you like this, Philip. This is a really tough problem. So here are some really tough problems. Okay. Okay. So what happens is to understand this at the quantum mechanical level, Again, I write down the potential x squared times ix to the epsilon times log of x squared, and I let epsilon go to 2. And now what you find is that you are in a broken PT symmetric theory, not an unbroken PT symmetric theory. In fact, this is what the energies look like. And what you see is that epsilon equals 2 when you recover the Higgs model, the minus x to the 4 log x squared model. What you find is that there are only 4 real eigenstates, and all the rest of the energies are complex. So in fact, we are in a broken PT symmetric region. This is a paper that we just submitted to the web a few weeks ago. And what I would like to conjecture is that the world is in a broken PT symmetric state. Okay? This is to make sense of this Higgs, upside down Higgs potential, I want to argue that that Higgs potential is PT symmetric. But if you calculate the eigenvalues, there are only a finite number of real eigenvalues. All of the rest of the eigenvalues are complex. Now you might think this is a very bad thing because we're in a broken PT symmetric regime. However, if you actually look at the world around us, there are only about 4 stable states. And those are the electron and the proton, and maybe if the neutrino has mass, the neutrino, and that's about it. Okay? There are a few massless particles, but they can't decay, okay, because of kinematic reasons. Okay? So like the photon and the graviton. And the rest of the states have complex energies corresponding to the fact that they are decaying or growing. So when a state decays, its probability goes down. It corresponds to a complex energy. But the state that it's decaying into, that goes up. Okay? So you have states with positive imaginary parts and states with negative imaginary parts, and that looks very much like a PT symmetric description of the universe. Okay? I would argue that the universe is not described by a Hermitian Hamiltonian because there are complex energies, okay, but that it is in a broken PT symmetric regime. At least that's the conjecture based on this quantum mechanical analysis of the model. Okay? So thank you very much for listening. Go away and please work on PT symmetric quantum mechanics. Thanks a lot. A host is an army. Don't bring an army. That's the last thing that we needed.
Okay, let me mention to everyone, I'll be talking tomorrow on a claim that every Hamiltonian has to be PT symmetric.
Philip, that is not a question.
Yes.
That's an announcement.
No, my comment is, all of the experimental results that you've obtained, people were trying to hook up PT symmetric systems that they could do experiments on. And I'm saying that they were able to because nature requires that every theory be PT symmetric, and you couldn't fail to get the results that you got. In other words, you don't have to artificially create systems. Anything that will work is going to work because nature requires that you do so.
I iterate.
Yes.
That was not a question. That was an announcement.
I said it was a comment.
Yeah, okay.
Okay. All right, now then, I've got lots of other comments that may be redefined.
No, not comments. Only questions.
They've all been transmuted into comments.
Okay, I don't know what to say, but am I not allowed to express the thoughts that have occurred to me on the basis of your talk?
No, but it's in the
Okay, all right.
doesn't expect.
I did want to make this issue of instability. I don't think that the question of having a state of lowest energy is the right argument to begin with. And the reason is that when you couple a system to gravity, energy is no longer defined. What you can define as an instability is, say, a tachyon in a propagator. which tells you that you're in the wrong Hilbert space.
Of course.
Yeah. So-
Okay,
and I
but
think that's the
okay,
better
but
way
what
to
I'm
go.
talking about here is something much simpler. I'm
Yes.
just describing an isolated system, and what I want to argue is that instabilities, primarily, we understand instabilities to mean energy, a situation where you have a potential where something is going downhill as you move away from the origin, and the typical image that I have is that you balance a pencil on the point, okay, and this is unstable, or you put a marble at the top of a hill. And what I would argue is that in some cases, when you put a marble at the top of the hill, in fact, it isn't unstable. The system is not unstable. That's I think, a novel interpretation, and complex variables, you cannot understand that interpretation unless you use complex variables. Just what I want to say is that if you are only knowledgeable about real variables and you have the function 1 over 1 plus x to the 4, okay, that function is a perfectly smooth function of a real variable. There are no singularities. That function goes all the way out to infinity on the real axis. It is infinitely differentiable, and yet its Taylor series has a radius of convergence of 1. Okay? And if a person who only knows real variable theory is confronted with this, it is a real puzzle. And in complex variables, we understand what is going on instantly, because we know that 1 plus x to the 4 has 4 roots in the complex plane, and they're at a distance of 1 from the origin, and that's the end of that. Okay? So what I want to argue is that complex variables reveals things about the real axis, which is very useful. Okay? But I think Stone should make a comment here.
Well, I actually don't, well, I guess it's a comment, but it's also a question. Which
Good.
Is, so, I mean, most of what we saw here was actually one-dimensional complex potential.
Mhm.
Potential. And some of this community has leaked over from those of us that work in quantum chaos. Okay, one of the thing that starts that field is that when you go to higher dimensions, you no longer can use classical paths to quantize. You no longer use force orbital quantization. You can perfectly well write down Hamiltonian with PT symmetry.
That's true.
You know, which has now, admittedly, it's at least you can do quantum mechanics with it, for eigenvectors, and then I guess the classical mechanics, you have to think a little bit about gain and loss. But so, I mean, I think that's just an unknown question. I mean, take a two-dimensional, I don't know, PT symmetric billiard or something like that.
Mhm.
From the analytic point of view, it's chaotic. I don't know what you can do. Do you have any thought about that? And have you see all this reasoning had to do with closed orbits and force orbital quantization?
No, that was really
Well,
an
heuristic.
yeah. I like giving intuitive and heuristic arguments, and you are completely correct. If you try to analyze that's what Philip raised during the talk. In a one-dimensional system, the way to intuit that there are going to be real eigenvalues is to simply look at the classical orbits and see if they're closed, and then use Bohr-Sommerfeld quantization to calculate those eigenvalues. But in a two-dimensional system, such as billiards, or as soon as you go above one dimension, now things are much more complicated. Absolutely, and the classical orbits are not closed because a particle can go bouncing around inside of a billiard box and never close. Furthermore, that classical orbit can be almost periodic or it can be fully chaotic. Okay, and this is very, very interesting. We have looked at such systems a little bit to study them, and just a comment about that. You can make just in the systems that you were looking at, if you look at interesting higher dimensional dynamical systems, what you can do is this. You can look for a dynamical system that has has loss. For example, it has a spiral point where trajectories are disappearing into the spiral point, okay? And you can put on gain, you can have another spiral point where trajectories are going out of that spiral point. And if the strength of those two spiral points are the same, okay, and you couple them, now you can have a dynamical system, and this is a system, for example, that describes chemical processes. Okay, this describes the concentration of various chemical reagents. Okay, and you can do this in the laboratory. And now you can look at the trajectories, and this is PT symmetric. It has a balanced loss versus gain, and you can see a transition between chaotic and almost periodic orbits, and you can see the breaking of PT symmetry. Okay, you can see instabilities appearing, but you are completely correct. It is much harder to see them at an intuitive level and to see what is going on and to know that the eigenvalues are going to be real.
At an analytic level,
At
you have good mathematical analyses of these 1D potentials, which seem quite rigorous for
Right.
limited knowledge.
Right.
But I don't know what you can do in 2D.
It is indeed really hard, and we could leave it there because it really is hard. This is hard work. There's lots of homework. Yes, go away and work on. Yeah.
You gave that example of two coupled oscillators as possibly the simplest example of PT system.
Yeah.
You supply energy to one oscillator, remove
Indeed.
the other, but then you have external forces.
Exactly.
Problem. Hamiltonian is time dependent. I mean, it's
No, well-
clear, the physics is clear, but what is the point of calling it?
Well, it's
You know that many oscillators can sustain
it's not a time-dependent
stable oscillation.
No, it's not a time-dependent Hamiltonian.
Yet you have an external force, right?
Yes, you have an external. There is a,
Dependent.
but it's not a time-dependent.
You're kicking one oscillator, so then maybe you can.
No. But it is not a. It's not a time-dependent Hamiltonian. The Hamiltonian, I can go back and show you. The Hamiltonian is explicitly not. You want me to go back and show you?
Do you kick at least one of the oscillators?
No, it's not. So in the laboratory, we did kick the oscillators, okay. But if you study it at an analytical level,
I'm asking Robert.
oh,
What was the experiment?
the experiment was a time. You are correct that in the experiment we did kick the oscillators as a way of taking energy out and putting energy in. That's how we did it. But so, for example, if even for this system here, okay, this is a PT symmetric system, and we can put in a coupling term, okay, and this is what the Hamiltonian looks like. It's time independent. Okay, so the abstract Hamiltonian, if you want to actually do this in the laboratory, you may indeed have a time-dependent Hamiltonian if you want to kick the system. But theoretically, I mean, this is a time-independent Hamiltonian. Yeah. So here, this is the equations, the theoretical equations, and in the electronic experiment, you didn't kick it. In fact, you didn't really have a.
At the end of the day, you see, my point of view here is the following. Even when you are writing in optics gauge, you put this I gamma, but what is this I gamma?
But on
It's
a
a
microscopic,
process,
microscopic.
and then you prefer to close your eyes on this and say that it is described in that way.
Saying there are no PT symmetric Hamiltonians on a microscopic level. It's always some phenomenology.
Well, that's true. There are.
Just like there are no atheists in a foxhole.
How far in optics, we're just hiding in an effective theory some other degrees of freedom.
Sure.
But the point is, so from our point of view, A and minus A are hiding the degrees of freedom that are either
Right.
sucking energy or.
Right. I mean, the question is how in the laboratory do you really do this? You know, what is this friction force really? And can you do it in a continuous time-independent way? And this is not so hard to do. Okay, you can have the system constantly under a continuous friction force that is not changing in time. This is hard to do, However, it can be done, and in the second of the optics experiments, it was done in a continuous way. Okay. However, if you really want to have the system be time independent in the laboratory, you can do that, because you can just get rid of this term completely. And then, although this system is not explicitly PT symmetric, it is a mapping of a PT symmetric. It's a simple transformation from a PT symmetric system.
Well, in
So
optics, when we have gain, there is exponential amplification.
that's right.
But here,
Sorry?
you don't have this. I wouldn't call this gain. You supply energy. That's true.
Yeah, I mean, I'm supplying energy to the system, okay, but it's undefined how I'm supplying energy. So this is correct, but okay, yeah.
Some other questions? Yeah. I'm outside the community, so I'm here some questions, and I still don't understand the main code, or maybe it's both. Is PT symmetric Hamiltonian is kind of the idea it's useful mathematical tool which for some effective systems can be used, or the idea is that maybe the nature is not does not have unitary, or that does not have Hermitian Hamiltonian basic like you talk about Higgs and whatever, so you have a hope that everything is started with PT symmetric and not Hermitian?
Well,
what is the hope of this?
Okay, I mean, let me just say, I mean, you've asked the hardest question of all. Okay, I mean, that's a really good question. You have to make me a promise that the next time you go to a string theory talk, you'll ask the same question. But so you can write down these PT symmetric non-Hermitian models, okay, and you can make materials that are PT symmetric, artificial PT symmetric metamaterials, and that is what has been done in optics experiments and in fact in Bose-Einstein. I mean, I hope to see some experiments. That'll be absolutely fantastic. I mean, there have been lots of studies of making PT symmetric systems where a Bose-Einstein condensate flows into a well and flows out of the well, and there's loss and gain and so on. Okay, but I agree with you that these are artificially constructed systems, and the bottom line, the really hard question is there a smoking gun in nature where you need to use a PT symmetric description? And Philip is going to give an argument that on the basis of Lorentz invariance alone, okay, on the basis of Lorentz invariance, the Hamiltonian must be PT symmetric, whether or not it is Hermitian. Okay? And that is coming close to answering the fundamental question. Of course, I hope that it turns out that that it will be necessary to describe nature using PT symmetric Hamiltonians. Now, this is this issue is, the final remark is, this issue is a little bit blurred because there is, and I didn't discuss this in my talk at all, but you can show that for a finite dimensional PT symmetric system, that is a matrix Hamiltonian, there exists a mapping, a similarity transformation. And if you take the Hamiltonian and you multiply the PT symmetric Hamiltonian H, and you multiply it by a matrix S, let's say, H S inverse, you get a new Hamiltonian which is conventionally Hermitian. Okay? However, in a continuous system, and that in fact was studied by Geyer and Schultz a long time ago, and in fact it was even studied by Dyson back in the 1950s. This idea was recognized as early as the 1950s. However, the problem is that this operator S that you multiply the Hamiltonian by is an unbounded operator. It is not a unitary operator. And therefore, what it does in the PT symmetric system is that it takes some vectors in the Hilbert space and maps them out of the Hilbert space. The PT symmetric system conserves probability. It is a probability conserving system, even though the Hamiltonian is not Hermitian. If you then map it to a Hermitian system, some vectors get mapped out of the Hilbert space. Okay, and you can map back and forth between the Hamiltonians at a formal level, the Hermitian Hamiltonian and the non-Hermitian PT symmetric Hamiltonian. But vectors can go in or out of the Hilbert space. And physically, I don't know what this means, and I don't know whether or not it is correct to say that there's an equivalence. And so this is very muddy water, at least in my mind, and work needs to be done to really clarify that issue. Okay, and the question is on the issue of, is PT symmetry really new and different from conventional fundamental quantum mechanics? I don't know the answer to that question. It's a very, very hard question.
So you do hope that there will be PT symmetric Hamiltonian, which is not Hermitian.
Yes, yes, and that is certainly true at a formal level. But okay.
Just a second, Yogesh and then Miroslav, and then we go.
Or I guess a related question.
Mm.
So, you just mentioned, for example, I guess the question is for optical systems, I understand, or I think about PT systems as effective Hamiltonians.
Mm.
Their time evolution is calculated using normal inner product, and therefore probability is not conserved, but it's okay, because it's an effective Hamiltonian.
Right.
A photon number is going to change, it's not going to be constant with time.
And you can do that, and that's fine.
Yeah, but the
I want to just emphasize.
But that is
really
using-
matters, okay, so you can't really say that we're going to define a different probability and so on. The actual number of photons or the photon flux is not conserved.
The number of photons is not conserved, but there is a strict definition of a probability, and that is conserved. That's very, very important. So it is conserved, and in fact, okay.
I guess what you're talking about is if the evolution is calculated using the CPT in the product. In that case, the probability defined with the CPT.
With the CPT inner product, that probability is conserved.
Right,
Yes.
but that one, so my specific question would be, for example, which of these works in nature? In other words, let's say if I take the Lee model that you were talking about, is it a physical model in the sense of predictions of it correspond to nature, or is it a mathematically well-defined model using a CPT inner product, which may or may not be the inner product that nature uses for a completely closed system?
Well, in the case of the Lee model, surprisingly, it's not a bad description of quite a few things. In fact, Weinberg studied in the Lee model, he said, let's take a V particle and an N particle and look at a bound state. Okay? And this is sort of like deuterium, proton and a neutron bound, exchanging a theta particle, and you get numbers that are pretty good. Okay? It's not bad, given that it's a very, very cut down, very basic picture of particle physics. It's not bad. Okay?
But these calculations were done using the deduct inner product, right? Not the inner product under which the Lee model does not have the problem.
Well, what he calculated in that case was not a probability. He calculated an energy, and the energy is not bad. It's not a bad description of the binding energy of deuterium. It's not bad, okay? But in answer to Stone's question, so this is a typical example, okay? This is a PT symmetric system, okay? And you can say, wait a minute, this cannot possibly be a Hamiltonian system. Can't possibly be. Because what you think of as the energy is clearly not conserved. When you look at an oscillator, you think of the energy as a combination of potential and kinetic energy. And the kinetic energy would be x dot squared plus y dot squared. And the potential energy would be x squared plus y squared. And that is obviously not conserved. Why is that? Because this system has loss, and so x, if we just throw away the coupling, Just throw the coupling away completely to simplify it. Then X is oscillating and dying out to 0, and it dies exponentially fast. Y is growing exponentially. So obviously the sum of the two is going out of bounds. So how could this possibly have a conserved energy? But Mr. Stone, it does have a conserved energy, and you have to define it correctly. And the energy is, this is described by a time-independent Hamiltonian, okay? And that Hamiltonian, the energy is not what you would naively think of as an energy. It's not x squared plus y squared plus x prime squared plus y prime squared. It isn't. It's another quantity, and that is conserved, okay? So the energy for this system is always conserved, whether or not PT symmetry is broken or unbroken. But what you see is that if epsilon is large enough so that you're in the unbroken region, then what you see is something in addition to the conservation of energy. You see that the system is in equilibrium, which means that y and x are not dying or running away, blowing up, but rather they're just oscillating. They're just oscillating around. And you can see that transition from non-equilibrium to equilibrium. But energy is always conserved, and you have to keep in mind that it isn't your intuitive classical picture of what an energy is. It's something else.
So you just can't do that, okay? So I'm playing with real photons.
Right.
And I put a calorimeter, and I
right.
measure energy.
Right.
It's we know that it oscillates.
Indeed. And what you measure...
PT unbroken phase, we sometimes see additional energy, sometimes we see a deficit, and on average it's constant. It's a very interesting observation about real energy. And
right.
you say there's some other quantity which is not measured by a calorimeter and is not measured by number of photons, which we could somehow measure and would be constant, but it
That's
doesn't
right.
have the meaning of energy.
That's right. You can call it something else. You could call it pseudo energy or stone energy or something like this. But the point is that's exactly right. The number of photons, which is what you normally measure, this is not conserved. You're absolutely correct. It's true. But there is a quantity that is conserved, and there's also a probabilistic interpretation, and you have a flow of probability current and so on. All that works, okay? And you have unitarity in the CPT norm, okay? Can I make just Yogesh, so just to say that one of the physical systems that I didn't mention is in fact systems in fluid mechanics, where you can take a cavity and have fluid. This is what you've studied. You can have fluid flow in, and you can have fluid flow out. This is very beautiful work, and you can see a transition. You can have a PT symmetric configuration, and you can see a transition from broken to unbroken symmetry. That's beautiful work. Really, really nice work.
One last question
I have to comment to Yogesh.
by Miloslav, and we have to, maybe you could ask him to come in time with us.
Yeah, in T.
We are running
Otherwise-
out of time. So.
Because we are running out of time, so I will just make a very short announcement that answer to your question about the smoking gun things. One of possible indications will be given in my talk, which is the last one of the conference. And just 1 second statement. Example of where you need non-emission thing is when you would like to oppose Ashtekar's concept of non-existence of Big Bang, because Ashtekar came to the conclusion that, based on various arguments, we cannot have Big Bang in cosmology. So he introduced the concept of big bounds, that the universe is in fact not coming to Big Bang, but it is just avoiding it. And if you want to stay in Dirac hermeticity, you cannot do anything else. And it was a very natural conclusion by Ashtekar and his group. It became popular and developed in cosmology and everything. But if you introduce this new inner product, you in fact use non-Hermitian operators which allow a real exception point. If you have in space of parameters a real exception point, because for Hermitian operators all exception points are complex. So the basic feature of non-hermeticity is that it allows real, which means experimentally achievable exception points, and this gives the way how to explain Big Bang as something compatible with textbook quantum mechanics. But time is
Yeah,
wasted.
but applying quantum mechanics to the whole universe is something
something different. I don't know what quantum gravity is, if it exists. Many things we don't know. Yes. Socrates at the time. Okay, I'm a very bad type myself. So next talks I will have to be more cool and stop questions at time. So
But I did finish on time.
you did finish on time. Indeed you did. So and